Here is another way to compute the sum of the numbers from 1 through n. This uses an unusual approach that you may need to think about for a little while to make sure it works. But essentially what we do is rather than incrementing sum by I as we're stepping through I from 1 to n, we instead increment sum by 1 and do that I times using this loop here. So the result of this inner loop is that sum gets incremented by I, which is like the program you saw before. And the reason we're doing it this way is to illustrate how to analyze different runtimes and the cost of different runtimes, different computational complexity formulas or different growth functions, as the book calls them. So this computes the sum of the numbers from 1 to n. How long does it take to execute? So this line here costs 1 and sum equals 0, and it executes 1 time. This line, actually, let's move that over a little bit. So this line costs 1 and executes 1 time. This line costs 1 and is going to execute n times, and we'll show that more in a moment when we draw the loops. This line costs 1 and is going to execute n times and also j times, as we'll see. And this line costs 1 and is going to execute n times and j times. And then this line costs 1 and executes once. So if we draw out the loops, which makes it a lot easier to think about this, we can see that everything inside these braces executes n times. So I'm going to draw that like this to show everything from this line through this line executes n different times. So times n, the cost of 1 times n, this cost of 1 times n, this cost of 1 is going to be multiplied by n, this cost of 1 is going to get multiplied by n. Then that takes care of the outer for loop, but we have another for loop in here. And so everything inside here is going to execute not n different times if we look carefully at the variables, but it's actually going to execute I different times. So each of these inner lines will execute I different times, and will execute I different times, and this whole loop, including the loop control statements up here for this other loop, will execute n different times. So all in all, these lines will actually execute I times n times. But before we look at that, whereas we can say, yes, these lines execute I times, we can also say the biggest value that I could possibly be is n, right? I is less than or equal to n. So instead of saying that these lines execute I times, we can say they execute no more than n times. And this is an example of thinking in a worst case analysis kind of way, which is actually what it turns out we're doing when we use big O notation. We're analyzing the worst case runtime. So each of these lines executes n different times, executes at most n times as we're going through this loop, and then this outer loop makes that n different times happen n different times as well. And so the result is, whereas this line only occurs n times, because it's in one loop, this line occurs n times for the loop up here, and also n times for the loop that it is. So this is going to happen n times, this is going to happen n times. And so the result is actually that it happens n times, or n squared times. And likewise, this line is going to happen n times because of the outer loop, and within each of those n times, it's going to happen n times because of the inner loop. So again, 1 times n, or n squared. So everything within this loop executes n times. But each time that we go through these lines inside this loop, that is, each time we go through the statement or sequence of statements within here, this loop is going to cause everything within it, as well as these parts of it, to execute n times. So each of the n times here, this is going to happen I times, or no more than n times. And so everything in here is really going to happen n squared times, and that's why we have this out here. So now, if we add up our runtimes here, we have 2 n squared, because this is n squared and this is n squared, plus n, because these two statements execute n times. We could have written 2 times n, it turns out it comes the same. And then these two statements, this one and this one, each execute once, so 1 plus 1 is 2. And so the exact runtime is 2n squared plus n plus 2. And the dominant term there is n squared. So when we write this using big O notation, we say this is equal to a big O of n squared, because this function grows at the same rate within a factor of a constant as any function that is n squared. And so it grows with a curve that is relatively sharp like that. So then we see that this implementation of the sum function, the one with 2 loops, has a runtime of O(n) squared. And indeed, generally any time that we have 2 loops, the runtime will be O(n) squared when we have a loop within a loop like this.